Hello everyone, welcome to this lecture series on sequence and series. Today we are uh, going to talk about some of the more tests regarding convergence of infinite series. As you remember in the previous lectures, we have learnt about the convergence by using some methods like geometric series, P series, harmonic series, and some others. Today we are going to test the convergence of many more series by comparing okay, their terms to those whose convergence is already known. Okay, so like uh, we know that the series of 1 by n is divergent harmonic series, or series of 1 by n square is convergent by p series test. So those series we know the convergence. Okay, so if you are given some uh, other series, but if we can compare those two series like p series or harmonic or some geometric series, then by comparing we can prove the convergence and divergence of other series as well. Okay, so let us take this definition, the comparison test. This is also called the direct comparison test, and it says that let there be series of non-negative terms. So let there be a series an, okay, then that there be another series bn, and there is a third series cn, and all these three series are series with non-negative terms. Okay, so that means ans are greater than equal to 0, all bns are greater than equal to 0, and all cns are also greater than equal to 0. Suppose that for some integer capital N, okay, such that for every n greater than n this holds, okay, the terms bn's are less than equal to the an terms, and they are less than equal to cn terms, okay, after some point capital N. Then if the series of Cn's converges, then the series of An also converges, and so is the series of Pn. Okay, so that means the uh, series of the bigger numbers converges, then the series of all smaller numbers also converges. Okay, if the series of Bn diverges, okay, then the series of An also diverges, and so is the series of Cn. Okay, so if bn's, okay, they are smaller than a and cn, okay, if the series of smaller numbers it diverges, then the series of bigger numbers also diverges. Okay, so the concept is simple that if c a series of cn converges, then because it's a series of non-negative terms, then by definition that the nth partial sum of the terms of Cn, it will be bounded from above. Okay, and if Cn's are bounded from above, then so because of An's are less than Cn, so An's are also bounded from above. So the nth partial sum of An's is also bounded from above, and because it is non-negative term, so partial sum is non-decreasing and bounded above from above, so it is automatically converging. Okay, similarly if the series of bn diverges, okay, that means the partial sum of bn's are not bounded from above, and because an's are bigger than bn's and the partial sum of bn is not bounded from above, then the partial sum of an's cannot be bounded from above, and so the series of an also diverges. Okay, say for example the series given this 5 over 5n minus 1n from 1 to infinity. Okay, now this is an is 5 over 5n minus 1, and we can write it as 1 over n minus 1 by 5, and so these terms are greater than 1 by n. Okay, and because this 1 by n we know its series is divergent harmonic series, and 5 over 5n minus 1 is bigger than this. Okay, so if you have a smaller series of smaller is divergent, then the series of bigger is also divergent. So this series is divergent by this comparison test to the uh, harmonic series. Okay, So because this series terms are bigger than the harmonic series, and harmonic is divergent, so this is also divergent. Because that's what it says. Okay, because Bn is divergent, so An is also divergent because An is bigger than Bn. Okay. The second um, another way to test this is the limit comparison test. Okay. Suppose that ans are positive and the terms bns are positive for all n greater than equal to capital N. Okay, so after some point the ans and bns are positive. Okay, so and if limit n tends to infinity, an by bn. Okay, so when n goes large, the ratio of ans and bns, if it this limit tends to some point, positive point, say c, okay, then the behavior of both series an and bn remains same. That means if one converges, then other also converges. If one of them diverges, then other also diverges. Okay, so if cn and a series an and series bn both converge or both diverge, say they behave exactly in the same way. Okay, so that means if you are given any numerical where you are given to test the convergence of some series, okay, then if we can choose another series bn whose convergence or divergence is known to us, and such that this holds that limit n tends to infinity, nth term of the series which we have to test and the nth term of the series which we chose, if its ratio is some positive finite number, then both the series will converge or diverge together. And because we have chosen bn such that its convergence or divergence is known, okay, so automatically we will know the convergence or divergence of the given series. Okay, the second formula in this line is that if this n tends to infinity an by b and this ratio is exactly 0, okay, then if the series that we chose, the denominator series bn, if it converges, then the series an also converges. Okay, and the third is that if this c is not finite, it goes to plus infinity. If the limit n tends to infinity, an by bn is plus infinity, then if the series of bn diverges, then so is the series of an. Okay, so there are three formulas that you can remember, that if we calculate the limit of the ratio, if that limit is finite positive, then both series will converge or diverge if the limit of ratio is exactly 0, and if series bn converges, then an converges. Okay, so it do not say that if the ratio is 0 and bn diverges, then an diverges. That is not true. Okay, that is that we cannot say. But if ratio is 0, when n becomes large and the series bn converges, then an also converges. Okay, only this much we get from here. Similarly, if the ratio when n goes large, if it becomes infinite and series bn diverges, then this series an also diverges. Okay, but if you get infinity as limit and series bn is convergent, then this test do not tell us anything. Okay, so we have to use the test exactly in how it is written. Okay, we'll just prove this. Okay, so for the first case, okay, since limit n tends to infinity, an by bn equals some value c positive, so by definition of limit, uh, there exists a epsilon positive such that for all n greater than n, uh, the modulus of an by bn minus c must be less than epsilon. Okay, so if we choose epsilon to be, say, c by 2, because c is positive, so c by 2 is also positive, there exists an integer n such that for all n, when n is greater than n, this will hold. Okay, with epsilon chosen as c by 2. Okay, and if we solve this right hand side, so we can easily write that an lies between c by 2 bn and 3c by 2 bn. Okay, so it immediately gives us that both an series and bn series will converge or diverge together. Okay, because if the series bn is convergent, then we know that any constant times the series convergent series is convergent. So 3c by 2 on the series Bn is also convergent. Okay, and so by direct comparison test, okay, any series which is smaller than a converging series is convergent. Okay, so the last definition we did. Okay, so if Bn series converges, then by right inequality the series An also converges. Okay, and if Bn series diverges, then the constant times the divergent series is divergent. So C by 2 times Bn series also diverges, and by comparison test any series bigger than the divergent series divergent. So by left inequality the series An also diverges. Okay, so that means series An and series Bn either both converge or both diverge together. Okay, if this holds. Okay, so that's proof of one. For second case, if limit n tends to infinity, an by bn is exactly 0, then again by definition for every epsilon positive there exists an integer n such that for all n greater than n this holds that an by bn minus 0 is modulus is less than epsilon. Okay, so that means the uh, ans are less than epsilon times bn. Okay, so we can just rewrite this. Okay, and so it immediately gives us that uh, if the series Bn is convergent, then epsilon is any positive number. So epsilon times series Bn, epsilon Bn series is also convergent, and ans are smaller than this. So the series of ans are convergent by the comparison test. Okay, so bigger series converges, smaller also converges. Okay, so this implies the second result that if the series Bn converges, okay, then the series An also converges. Third case is if the limit n tends to infinity, an by bn is infinite. Okay, so by definition, for every positive number there exists a integer n such that for all n greater than n, this number is bigger than b. Okay, so an by bn's are still bigger than b. That's why this limit goes to infinity, because there is no upper bound. Okay, for you choose any large number, the ratio is still larger than that. Okay, and so from here we can write that an is greater than b times bn. Okay, and so if this implies that uh, if you have a known series Bn which is divergent, then this number times Bn is also divergent, and any series which is bigger than a divergent series is a divergent series. Okay, so series Bn diverges immediately implies series An diverges because the terms An are bigger than the terms Bn. Okay, by quantity b times Bn. Okay, so this is the proof of the limit comparison test. So if you are given some series A and C, and if you can compare it with some series known series Bn whose convergence divergence is known, and if you can prove the ratio of the limit as finite positive, then immediately you can have the convergence divergence of A and series. Okay, or you can use second or third case if you find limit 0 or limit infinity. Okay, say for example, does the following series converge or diverge? So here we have 3 by 4 plus 5 by 9 plus 7 by 16 plus 9 by 25 plus so on equals to this can be written as infinite series sum of 2n plus 1 by n plus 1 squared, where n varies from 1 to infinity. That means if I plug n1 we get the first term plus n is equal to 2 second term plus third term plus 4 sum and so on. Okay, so we will apply here limit comparison test. Okay, given this series, so we know what is an. Okay, an is 2n plus 1 over n square plus 2n plus 1. Okay, so to apply limit comparison test we have to choose another series of bn. So we have to define what should be our bn. So now how to do that, how to find that bn is important. Okay, so by looking at the AN series, what you can first try to locate is that what are the dominating terms in this series. Okay, so when n becomes large, what are the dominating terms in the numerator and what are the dominating terms in the denominator. Okay, so when n becomes large, you can see that this term 2n will dominate a constant number. Okay, so in the numerator 2n is the dominating term. Okay, similarly when n becomes large, the n square will grow much faster than any this linear or constant term. So n square is a dominating term. Okay, so this series, these terms an's, when n becomes large, will behave like 2n over n square. Okay, or like 1 by n. Okay, n over n square. So we can choose in this case bn to be simply 1 by n. Okay, the dominating term from here and dominating term from denominator, its ratio. Okay, so 1 n over n square, which is 1 by n. Okay, and so we have a series of bn which is summation 1 by n, and we know that it is a divergent harmonic series. Okay, so if the limit of ratio is finite positive, series of bn is divergent, so series of an will be divergent. Okay, so let us calculate what is limit n tends to infinity an by bn. So limit n tends to infinity, an is this. Okay, and bn is 1 by n, so it becomes n over 1 because it's in the denominator. And so I can take n square common and cancel out or rewrite this as limit n tends to infinity of this, and when n becomes large, you can see that the value comes out to be a 2, which is a positive number. Okay, positive finite number. So it's a case 1 of the limit comparison test, which says that if limit n tends to infinity an by bn is positive finite number, then if the series an and series bn both uh, either converge or both diverge. And since we know this series of Bn is a divergent harmonic series, so that means that series of An will diverge here. Okay, series both converge or both diverge because of case 1, and because series Bn, which is series 1 by n, is divergent harmonic series, so series An also diverges. Okay, so now I hope it is clear how to utilize this test. Okay, so given series, you choose another series of bn's and just check the limit, and then you can use the limit comparison test to decide on the original series. Okay, so say take another example. Does the following series converge or diverge? Series is n is equal to 2 to infinity 1 plus n ln n square plus 5. Okay, so now here again we will use this limit comparison test to check the convergence and divergence of series. uh, an's are given 1 plus n log n over n square plus 5. uh, to choose bn, uh, let us see what are the dominating terms here. Okay, in the numerator, when n grows, n log n will dominate other term, which is 1. Okay, so n log n is the dominating term in numerator, and n square is the dominating term in denominator. When n goes large, this term will grow and it will dominate 5. Okay, so the ratio of dominating terms is as n log n by n squared. Okay, which is simply log n by n. Okay, so you can choose bn as log n by n. Okay, or in this case we are also saying that log n by n, it is greater than 1 by n. Okay, for n greater than equal to 3, because we know that log n is greater than 1 for n greater than equal to 3. Okay, so we are going to choose bn as 1 by n. Okay, because if because we know this is a harmonic divergent series, so this one will also diverge. Okay, so if we compare these two, we'll come to know whether it is converging or diverging. Okay, so choose bn to be 1 by n. Okay, and if we calculate the limit comparison test, limit an by bn. Okay, so limit n tends to infinity, an by bn will be uh, an over bn, so bn becomes n by 1. Again we can take n square common and rewrite this. Okay, so log n plus 1 by n over 1 plus 5 by n square. So when n goes large, is 1 by n and 5 by n square are 0, but log n becomes infinite, so it gives us the value infinity. Okay, so limit a on the ratio is infinite, which is case c third. Okay, of the limit comparison test, and which says that if the series bn diverges, then an also diverges, and we know that bn is a divergent harmonic series. Okay, so an is also a divergent series. Okay, as I said, we choose bn as 1 by n. Okay, but you could have also taken bn to be log n by n. Okay, in that case uh, here we would have substituted n by log n. Okay, so this could have been rewritten because log n will be divided here, so it will be 1 plus 1 by n log n. So when n goes large, these two terms will be 0 and we'll have here 1 by 1. So this number would have come to be a 1, which is a positive finite number. So case 1, if we choose bn to be log n by n, and by case 1 the series an and series bn will converge or diverge together. And because again this is greater than this, by direct comparison test, if smaller series diverges, bigger diverges. Okay, so we know this is a divergent series and both converge diverge together by case 1, so this is also divergent. So in that way also we can prove that the series an is divergent series. Okay, so now I take another definition here. So far uh, what we said is we did numericals based on the series where all the terms are non-negative terms. Okay, but what will happen when some of the terms of a series are positive and others are negative? In that case the series may converge or may diverge. Okay, depending upon how the behavior of the terms are. Okay, so the concept of absolute convergence can be used to test the behavior of series where you have some of the terms as positive and some of the terms are negative. And this definitions of absolute convergence says that a series an, okay, where the terms an can be having positive terms as well as negative terms. It converges absolutely, or we say it is absolutely convergent, if the corresponding series of absolute values of an converges. Okay, so if we take the modulus of all the terms, that means if we construct a corresponding series of non-negative terms, then if that series converges, then the original series, which contains positive as well as negative terms, is also convergent, and we say it is absolutely convergent. Okay, so and to test the series of these absolute values, we have done now so much uh, test. We can use p series, harmonic, geometric series, comparison test, or limit comparison test. Okay, so all those tests we can utilize to check the convergence of series of absolute values, and if it converges, then the original series also converges. Okay, but it do not say anything about when this the series of absolute values diverges. Okay, so even if the series of absolute values diverges, the original series, which is a series of positive negative terms, may converge. Okay, so we cannot decide from there. But if the absolute value series is convergent, then definitely the original series is going to converge. Okay, and so we have a important result from here, the absolute convergence test, which says that if the series of absolute values converges, then the series converges. Okay, so if you are given any series an which may contain positive or negative terms in between, so if we construct a series of absolute values from there, and if we prove that it converges, then the original series is definitely going to converge. Okay, so we'll just prove this result first. Okay, this theorem, we know this is always true for any n. Okay, uh, an plus the absolute value of an, this is always greater than equal to 0. Okay, if ans are positive, so this will be a strict positive. Okay, it becomes 2 times an with an non-negative, non-zero. And if ans are negative, so these two will add up to 0. Okay, so this left inequality is always true. And because uh, any number is always less than its modulus, so an is always less than equal to its absolute value, so this sum is always less than equal to 2 times the absolute value. Okay, so this result is always true. uh, and now since this series is given convergent, okay, the series of absolute values, so if we multiply the absolute value by 2, then the series of 2 times the absolute value is also convergent, okay, by the result we already know, okay. And since the series of 2 times absolute value is convergent and it's a series of non-negative terms, so it must be bounded from above. And so this series of an plus modulus of an is also bounded from above, and so it is also convergent, okay. So if bigger series is convergent, okay, then this series of smaller terms is also convergent, okay. So this holds true. So what we have proved is from here that if the series of modulus an is convergent, then the series of an plus mod an is also convergent, okay. Now what is the series of an? Okay, we have to prove this. So if we start with this as a left hand side, we can rewrite this series of an by adding to it modulus of an and subtracting it, okay. And so this sum can be written as difference of these two, okay. So sum of, like, this is a, say, capital C, this is capital D, so sum of C minus D is sum C minus sum D, okay. And because both these series are convergent, this series of absolute values of an is already given convergent, and the series of an plus absolute of an, we just proved that it is convergent. So it is the difference of two convergent series, and we know that if two series converge are convergent, so their difference is also convergent, okay. So this immediately proves that the series an, which is the difference of two convergent series, must be convergent, okay. So that is the proof that uh, if you have a given series, you can test the convergence of its absolute values, and if the series of absolute values converges, then you can immediately see that the original series converges by this absolute convergence test, okay. So let us take, say, one example to show you this. What can be said about the convergence of this series n is equal to 1 to infinity minus 1 raised to power n plus 1 over n square. And so if you expand this into infinite series, you will see that it is this 1 minus 1 by 4 plus 1 by 9 minus 1 by 16 minus so on, okay, or plus so on. So this is the infinite series where you have terms which are positive and you have terms which are negative. So it contains both positive and negative terms, okay. Uh, to check the convergence of this series, what we do is we check the convergence of the absolute series of this, okay. So here if we write the series of absolute values of an is this, okay, minus 1 raised to power n plus 1 over 1 n by n square, that's the n, okay. So the modulus of this will be simply 1 by n square, okay. So modulus of minus 1 will be plus 1. So this series of 1 by n square, and we know that this series is convergent by p series test, okay. Series of 1 over n raised to power p converges for p greater than 1, and here p is 2, okay. So it's a convergent series. So series of absolute values converges, so by absolute convergence test, the original series, which is series minus 1 raised to n plus 1 1 by n square, this is also convergent, okay. Now I'm going to take two important tests here, which are the ratio test and the other is the root test. uh, the ratio test is also known by the name D'Alembert's ratio test, okay. And it says that if you are given a series an, which is any series, okay, so it may be a series of non-negative terms, or it may be a series which contains positive as well as negative terms, and suppose that this is true, that the limit n tends to infinity, the ratio of the absolute values of an plus 1 over an, okay, so an plus 1 is the n plus first term of this series and an is the nth term of this series, okay. If this ratio is a limit is rho, okay, where rho is some constant, then the series converges absolutely if rho is strictly less than 1, okay, if this value is strictly less than 1, okay. And so this series converges absolutely means that this series converges and its modulus series and the series of absolute values is also convergent. Okay, the series diverges if the row value is greater than 1 or row value is infinite. Okay, the test is inconclusive if we get the row value as 1. Okay, so if we get the limit of the ratio as 1, the test is inconclusive. Okay, so we cannot use this test in this case, and then we have to apply something else. Okay, so we'll prove this result first. So let us prove the first case, that let rho be less than 1. Okay, so let this limit is rho, and rho is less than 1. Let r be a number between rho and 1. Okay, so between rho and 1, let us choose a number r, and then define epsilon to be a positive, such that epsilon can be written as r minus rho, because r is greater than rho. Okay, so r minus rho is a positive. So by definition of limit, okay, since this limit is given, since limit n tends to infinity, this equals rho. So for epsilon positive, we can write that the difference of the modulus of these two is less than epsilon for all n greater than equal to some capital N. Okay, and what we used to say is, for every epsilon positive, there exists a capital N, such that for n greater than equal to n, this holds. Okay, so if we uh, open this modulus, okay, so we can write that the absolute value of this ratio is less than rho plus epsilon, and rho plus epsilon we have chosen to be r. Okay, so the absolute value ratio is less than r for all n greater than equal to capital N. Okay, so from here we can write that an plus 1, absolute value of an plus 1 is less than r times absolute value of an. So we can take this an to other side. Okay, and this holds for uh, all n greater than equal to this integer capital N. Okay, so this is true. Okay, so if we plug this here, n as capital N as capital N plus 1. Okay, because this holds for every n greater than this. Okay, so it holds for capital N, it holds for capital N plus 1, it holds for n value as n plus 2, n value as n plus 3, and so on. Okay, so if we plug n as capital N, then we get this. Okay, a of n plus 1 is less than r times absolute value of a of capital N. Okay, so just writing n as capital N here. Similarly, if I put n as capital N plus 1, then again this will hold. Okay, so we'll get is a of n plus 2, which is modulus less than r times a of n plus 1. Okay, so we just plug n as n plus 1 here, and because the modulus of a of n plus 1 we have calculated already, so we can substitute back, and so what we get is r square modulus of n. Okay, similarly, if I now put n as capital N plus 2 here, so it will give me a modulus of a of n plus 3, which is less than r of a of n plus 2, and because modulus of a of n plus 2 we just calculated as this, so we get is r cube modulus of n. Okay, so you see what is happening is, for n plus 1 we are getting r times, for n plus 2 we are getting r square times, for n plus 3 we are getting r cube times, and in general, if we calculate for modulus of a of n plus m, we will get that it is less than r power m times n. Okay, so for 1 it is r power 1, 2 r power 2, 3 r power 3, so for m it will be r power m. Okay, and so if we write the series of absolute values for k from n to infinity, okay, so for all n bigger than this, okay, n to infinity, then we can reindex it, okay, to m0 by simply putting k as capital N plus m. Okay, so if I put k as capital N plus m, so it will give m0 here, and k here also is there, so k as capital N plus m. So you know how to reindex series. Okay, so this is just reindexing, so these and these two are just same. Okay, so they will give the same terms. Okay, and uh, a of n plus m modulus, we just calculated it as less than r power n modulus of n. Okay, so we just plug this value here, so it is less than equal to m0 to infinity modulus of n r power m. Okay, and so when m goes from 0 to infinity, modulus of an is a fixed number, it goes outside the series. Okay, so we have series m0 to infinity on r power m, and we know that this is a geometric series. Okay, and so this geometric series, by geometric series test, it converges if r lies between 0 and 1. Okay, and that we already chose that r lies between rho and 1. Okay, so and this is true, so this series is convergent, and because this series is convergent, so and this series of k n to infinity of absolute values of ak is smaller than this, so this, by direct comparison test, this series of k n to infinity ak is also convergent. Okay, by comparison test. And since adding or deleting finite number of terms do not change the convergence or divergence property, so the original series, which is from k is equal to 1 to infinity on modulus, is also convergent. And if the modulus series is convergent, then the original series is absolutely convergent. Okay, so the series k is equal to 1 to infinity ak, or n is equal to 1 to infinity an, is absolutely convergent series for rho less than 1. Okay, so that's case 1 proof. For second case, if rho is greater than 1, or it can go to infinity, from some index m onwards, this ratio must be greater than 1. Okay, because if this ratio is less than 1, then if n becomes large, we say that this converges. Okay, so this an plus 1s must be greater than the ans. Okay, so if I take this to other side, modulus of an plus 1 must be greater than modulus of an for some n greater than equal to capital M. Okay, and then if I plug n value as m plus 1, m plus 2, so on, so I will get this result. Okay, so if I put n as capital M, so am modulus will be less than modulus of am plus 1, so that's first inequality. If I plug n as m plus 1, so modulus of am plus 1 will be less than modulus of am plus 2. Okay, so we get this inequality. Okay, and so combinedly we can write this. Okay, and so these terms do not approach 0 when n becomes large. Okay, because it's a series, these terms are positive absolute values and they are increasing. Okay, so with n becoming large, this will not tend to 0, and so the nth term test says that limit n tends to infinity an, if it is non-zero, then the series should diverge. Okay, so the nth term test for divergence says that the series will diverge if rho is greater than 1. Okay, so that's second case. Third case is that what happens when rho is 1. Okay, so here we have two counter examples to prove that there could be convergence or there may be divergence. Okay, so we cannot predict from here. Okay, so if we choose a series of 1 by n and a series of 1 by n square, we know that this is a harmonic divergent series and this is a convergent series by paired series test. Okay, so one of the series is divergent, other is a convergent series, and in both cases, if you calculate the limit n tends to infinity an plus 1 by an, you will find that it gives value 1. So rho is 1 here in both cases. Okay, but one of the series is divergent, other is convergent, so that means we cannot predict the result if the rho is 1. Okay, so the test is inconclusive in this case. Right, so this is a ratio test. You can utilize this to find the limit of the absolute values, absolute ratio, and then you can predict the convergence and divergence of the series. Okay, let us take one example here. Say, investigate the convergence of the series n0 to infinity 2 power n plus 5 by 3 power n. Okay, so let us use this ratio test to uh, prove or check this convergence. So given an this is series an, and an will be then 2 power n plus 5 by 3 power n. Okay, and for ratio test we need an plus 1. So next term, so if I put n as n plus 1 here, so we get an plus 1, which is 2 power n plus 1 plus 5 over 3 power n plus 1. and then we just need to calculate the ratio an plus 1 by an. Okay, and an plus 1 by an will be this number divided by this, so this will be written in the reverse order, and so we can cancel out 3 power n and just we can rewrite this. Okay, and so if we take the absolute value of this and take limit n tends to infinity of this, okay, so limit n tends to infinity on the absolute of this ratio, so limit n tends to infinity on this, and that gives us 2 by 3, and this value is rho, which is less than 1. Okay, so this immediately tells us that by ratio test this series is a convergent series. Okay, so by ratio test the given series converges because this limit is less than 1. Okay, uh, there is another test. Okay, sometimes ratio test fails, even then in those cases we can apply a root test. Okay, root test is said to be more powerful than ratio test, okay, in many cases. Okay, so let a series a and b any series. Okay, so again it can be uh, non-negative term series, or it can be a series which contains positive as well as negative terms. And suppose that limit n tends to infinity on the nth root, okay, nth root of the absolute values of n. If this limit equals rho, then the series will converge absolutely if rho is less than 1. Okay, that means this series will converge absolutely, means the its modulus series is also convergent. Okay, and the series diverges if rho is greater than 1 or rho is infinite, and the test is inconclusive if rho equals 1. Okay, so the results are same, but we are using a different way here. So instead of using an and an plus 1, we are simply calculating the nth root, okay, of the absolute value on an, and calculating this when n becomes large. Okay, so if this value comes out to be less than 1, we say convergent. If it comes out to be greater than 1, divergent. And if it comes out to be 1, then again this test fails to conclude anything. Okay, so let us prove this test as well. So let rho be less than 1. So case 1 we are going to do first. Okay, choose epsilon positive so small that rho plus epsilon still remains less than 1. Okay, and because this limit n tends to infinity equals rho, so by definition of limit there exists a integer m such that for all n greater than equal to m, this is less than rho plus epsilon. Okay, or you can say that this minus rho modulus is less than epsilon, and then we can rewrite that as this root is less than rho plus epsilon. Okay, and so if we take nth power on both sides, we can just rewrite that modulus of an is less than rho plus epsilon power n for all n greater than equal to capital N. Okay, and if you look at the right hand side, it is like some number power n. Okay, so its series will be a geometric series which is convergent because this rho plus epsilon is less than 1. Okay, so right hand side series is convergent series for n greater than equal to m. Okay, so the geometric series n is equal to m to infinity rho plus epsilon power n is convergent because rho plus epsilon is less than 1, and because absolute values of an are less than this for all n greater than equal to m, so series of this modulus for n is equal to m to infinity modulus of an, this series will be convergent. Okay, so by comparison test, n is equal to m to infinity modulus of an series is also convergent, and from here we can write that the series n is equal to 1 to infinity of modulus of an is this series plus some terms. Okay, and because adding some terms to a convergent series do not change the convergence, so this new series, which is by adding terms modulus a1 to modulus of am minus 1, this series is also convergent. So series n is equal to 1 to infinity n is convergent series, and if the series of modulus is convergent, so the original series an is absolutely convergent. Okay, so that's proof of part 1. For part 2, when rho is bigger than 1, So for all indices beyond some integer capital M, we have that the nth root of modulus of ans are strictly greater than 1. Okay, and this immediately implies that modulus of ans are greater than 1 for all n greater than m. Okay, and so uh, if this is true, then this is true that for when n becomes large, this limit n tends to an will be greater than 1, so it is not going to 0. Okay, so again by nth term test, okay, the series is divergent series if rho is bigger than 1. Okay, and for the third case, again we take the same two examples, series of 1 by n and series of 1 by n square. uh, if you check the uh, limit on the nth root on these two, then again you will find that the limit value is 1, that means rho is 1. But we know that this is a divergent series and this is a convergent series. So for again for rho is equal to 1, this test is inconclusive. Okay, so this is a root test. Okay, let us take one example. Say check the convergence of series is n is equal to 1 to infinity on 1 over 1 plus n whole power n. Okay, so we'll do it by a root test now. Okay, so let us solve this by root test. An is this, an is 1 over 1 plus n whole power n. Okay, so if we calculate the limit n tends to infinity on the nth root on absolute of n, so when we take nth root on this, we'll just get 1 over 1 plus n, and when n goes large, this value is 0. So limit value is 0, which is less than 1. Okay, so that means the root test says that the series is a convergent series. Okay, so this is very simple example to prove the convergence of series. Okay, so like we close this lecture for today, and I'm leaving you with some numericals to solve. Okay, in the first case, check the convergence or divergence by the ratio test for these three numericals, and in the second case use the root test to check the convergence and divergence of these three. Okay, so we'll continue with this, and in the next lecture we'll talk about alternating series and its convergence. Okay, till then, have a good day.